Hello and welcome back to New Scientist Weekly, your curated selection of the week's science stories. I'm Christy Taylor in New York.
And I'm Timothy Revel in Actually, I'm back in London, back in the mothership for a short little visit.
It's a surprise twist.
This week, big awards for tiny science at the Nobels, plus what earthly electrons have to do with water on the moon, and good news for chicken hatcheries trying to be more ethical. We've also got a fun mathematical puzzle for you to solve, and we'll deliver some bad news about the carbon footprint of internet from low Earth orbit.
But first, the 2023 Nobel Prize nominations have been announced, and the results for the science prizes reward researchers working at some of the smallest of scales. From the tiny mRNA molecules that quickly led to efficacious vaccines for the novel COVID-19 virus in 2020, to some of the shortest pulses of light that physicists have ever used, to dots of material so small that their behavior is affected on the quantum scale.
We've got medical reporter Claire Wilson and physics reporter Alex Wilkins here with us to talk about the results. Hello.
Hello.
Hi.
So Claire, this year's Nobel Prize in Medicine and Physiology, it went to two scientists who helped develop mRNA vaccines. What did you make of this? Did it come as a surprise?
Oh, well, actually, I did have this down as a leading contender, but I didn't write it down anywhere. I didn't tweet it, so I can't prove it. But I honestly had thought it. So yeah, the new Nobel laureates are Catalin Carrico and Drew Weissman for their discovery of how to chemically alter mRNA to allow it to be turned into vaccines. And that, of course, led to two of the main COVID-19 vaccines.
I feel like mRNA was one of those terms that before the pandemic, maybe we didn't use as much, but now it's just become part of everyday speech.
Yes, so if you've had a Pfizer-BioNTech COVID-19 vaccine or one from Moderna, you have benefited from this Nobel-winning technology. The COVID-19 vaccines as a whole are thought to have saved so many lives and prevented severe illness in so many more people. Millions of people around the world have benefited from this.
So what exactly was their discovery? What part of the process in the mRNA vaccine did they actually figure out?
Well, just to give a bit of background, mRNA. So this is a natural molecule. There are hundreds of thousands of copies of mRNA in almost all of our cells in the body. And this is a messenger molecule. It allows genetic information stored in our DNA that's kept trapped inside the cell nucleus. It allows that information to be transported to the protein-making factories in the rest of the cell. They actually do the business of making protein. They're called ribosomes. So you've got to get that information to the ribosomes somehow you can't move the DNA itself. Now, once we realized this, right from the start, there'd been interest in using mRNA to kind of instruct cells to make proteins that they would not normally do as a way of treating almost any disease you could think of. But they quickly realized that if you put artificially synthesized mRNA into the body, it looks very similar to RNA made by bacteria and so is destroyed by the immune response before it can get to work, because obviously we don't want bacteria in our bodies. So Carrico and Weissman's breakthrough was to understand exactly how bacterial mRNA looks different to our own mRNA or indeed that of any mammalian cells. And they understood how to chemically alter the artificial mRNA to disguise it, to make it look like our own mRNA.
There's so many really intricate steps to getting this technology that is, again, it now seems so commonplace for us. But I also understand that it's the case that these two scientists actually had a really hard time convincing people that they could get it to work, that it was even worth investing in. Is that correct?
Yes, and that seems amazing now we understand, the impact that it's had. But Carrico was working on this for the longest. She was appointed at the University of Pennsylvania in a non-tenure track position. She had to scrabble around for funding. She applied for many, many research grants and was turned down for them. She actually never won a single grant from the NIH, the National Institutes of Health, and that's, as you know, the major funder of medical research in the US. And it was only a chance conversation with Weissman at the photocopier that led him to ask her to come and work in his lab. And eventually they had some success and published what is now seen as a seminal paper in 2005. And in that, they showed how artificial mRNA could be chemically altered to avoid this destructive immune response. And that led to their patents being licensed by Moderna and BioNTech, where Kariko went to work, and the rest is history.
All right, stay right there, Claire. We're going to come back to you in just a minute. All right, Alex Wilkins, you're here. The Nobel Prize in Physics went to research that has applications in electronics and healthcare diagnostics, all while telling us about the behavior of electrons. Even, I think, allowing us to make movies of them. Tell us more.
Yeah, so this year's Nobel Prize for Physics went to Pierre Agostini, Frank Krauss, and Anne Lullier for their work on generating ultra-short pulses of light to study how electrons move through matter.
So why are electrons so hard to study, and why do the pulses of light have to be so short to do this?
So electrons and the way they move and the timescales they move on are on the scale of attoseconds, which you'd be forgiven for not knowing how short that is, but it's a billionth of a second, which again may not illustrate how short it is. To give some perspective, if you shine a flash of light, and light is the fastest thing we know traveling in the universe, from one end of a room to the other, it would take 10 billion attoseconds. It's impossibly, unfathomably short to comprehend. To take snapshots of electrons moving at this time scale, it's a bit like if you've ever been under one of those strobe lights at a concert and your body's moving in frames, and every time the light strobes, you see a different position in your body. Taking pictures of electrons at these timescales, the technique is the same. So you need pulses of light that are flashing on the order of attoseconds to really see them.
So we're throwing the world's shortest moving disco then for these electrons.
Exactly.
I saw one description of this attosecond order, that there are about twice as many attoseconds in 1 second than there have been seconds since the Big Bang, which is just one of those so difficult to comprehend what that is even talking about, to get a sense of it. But it just gives you a bit of a vague feeling of just how quick these ultra short pulses of light are. How did the Nobel laureates actually go about making such a quick pulse?
Yeah, so it wasn't easy at all. For a really long time, until the 90s, scientists thought there was a limit on how short we could make pulses at about 1,000 attoseconds, which is equal to 1 femtosecond. That was just how short we could make laser pulses, and it wasn't clear how we might get shorter ones. But in 1987, Anne Lullier and her colleagues found out that when you shine infrared laser light on one of the noble gases, so argon or neon or xenon, the light that the gas emits has this weird property of being a constant intensity, like the laser that was shone on it, but over a very, very short duration. The exact reason why is a little bit complicated. It's to do with harmonics, the same sort of reason that a champagne glass vibrates when you hit the right note. But basically, it meant that there were pulses of light short enough to go below this femtosecond barrier.
And then was it fairly straightforward from then on out?
Not at all, no. It still took decades of explanation from theorists, from Lullier and other scientists, and Pierre Agostini and Frank Krauss, the other recipients of the prize. They actually developed these new methods to control the length of the attosecond pulses and make sure that we could really sort of make them on command and control them for whatever we wanted to image.
I feel like you would have a lot to brag about just by saying, world's shortest pulse of light as one of your accomplishments. But there's also a use for this, right? Now that we can observe how electrons move and make movies of them, there are all these applications for it, right, Alex?
Yeah, absolutely. So being able to understand how electrons move through matter explains loads about the weird ways that matter interacts with the world and itself, because electrons are in everything. Some of the most prominent discoveries that have come from this attosecond electron studies are things like ultra-fast electronics, which could one day lead to development of really powerful computer chips. It's not quite there yet, but it's definitely on the way. And other things like letting us distinguish molecules from each other based on the electron properties within the molecules, which is being trialed for things like accurate diagnostic techniques for things like blood marker tracking. But really, the whole field is just getting started. Now that we can study electrons on these super short timescales, we're going to be able to describe how matter interacts with other matter and the world in unimaginable detail. It's really impressive stuff.
All right, Claire, so back to you for the chemistry prize, which is all about quantum dots. Can you tell us what they are and what made them Nobel Prize worthy?
Okay, first the winners. Two of the new Nobel laureates are Louis Brou and Alexei Ekimov, and they discovered the technology in the 1980s separately. And the third winner is Mungi Bawendi, who developed better techniques for making the dots in a very perfect, pure way later on. Basically, quantum dots are very tiny crystals made from a variety of chemicals, some of which are quite commonplace, you might have heard of, like lead sulfide, or there are other ones. Again, I need to try and get over how small they are, that they're only a few nanometers in size, less than 1,000th the width of a human hair, and they might just have a few thousand atoms in each crystal.
What's that in attoseconds? That's what I want to know. So why does this matter? Why do we care about very, very small crystals?
Yes, well, when you get that small, the strange world of quantum physics starts to kick in, and that normally only applies to things on the atomic scale. But within quantum dots, they're so small that electrons can only occupy discrete energy levels, and that means that if they are excited, they emit light at very specific pure wavelengths, and these vary depending on the properties of the crystal. And that means they have very, very pure colours.
So literally flashy science.
Yes.
That's really, really cool. So again, not that everything needs an application, but how could you exploit or apply quantum dots and these beautiful pure colors?
They're already being used in some commercial applications. So they're already being used in things like TV screens, lights, and lasers. They also have medical applications. For instance, they're being investigated as an aid to surgery for cancer, because if you link these quantum dots to certain targeting molecules that can home in on the cancer, and then you inject them into somebody who's about to have the surgery, they home in on the tumour cells and they glow very brightly. And that allows the surgeons to only take out the cancerous tissue during the operation and to leave behind other tissue. And of course, the more healthy tissue you can spare, the better for the person.
And I was asleep in the US at the time that all of this happened, but wasn't there some kind of kerfuffle about a leak for this Nobel?
Oh, yes. So it was all over the Swedish press very early yesterday morning. It seemed that somehow a press release from the Nobel Academy got leaked to a Swedish newspaper. So I knew that I was on duty to watch the press conference that morning that was due to be at 10:45, but I was just scrolling through my emails over breakfast, and I nearly spat out my tea over my phone, so I had to get to work quickly. And fortunately for me, a Swedish journalist friend had very kindly managed to get hold of this press release, and he sent it to me so I could crack on. But the Nobel Academy was denying that they had made their final decision, so we had a bit of a debate over whether to run the story before the official announcement. In the end, we did run the story, but we included their denial, and it turned out to be right, so that was the right decision.
Whoops. I mean, I feel like they're normally very, very good on keeping the Nobels secret, and I'm very skeptical about them leaving the decision till the last minute. Like there's an envelope with spotlight in one and quantum dots in the other. I don't think so.
Yes, I don't think we've got to the bottom yet of what happened there, but it turned out to be the right names leaked in the end.
On top of the most famous awards in science, there's also been plenty of other news this week, and one story that particularly caught my eye was that electrons from the Earth may be influencing the creation of water on the Moon. That's according to a new analysis of data from India's Chandrayaan-3 lander.
Tim, I'm really interested in the explanation of how that might actually happen, because last I heard, the Earth and the Moon don't actually touch.
Yeah, that's of course true. But particles, they have a way of sort of wafting across from one place to another. In fact, we already think that high-energy protons from the sun's solar wind participate in a sort of chain reaction with oxygen from minerals on the moon's surface, and that leads to the creation of water, since those protons, they don't need much else to become a hydrogen atom. But the moon, well, it still forms this new water during a full moon, which is when the Earth shields it completely from the flow of protons from the sun.
Well, that's a mystery then. Maybe a mystery as deep as the dark side of the moon.
All right, David Gilmour. Yeah, it turns out that when the moon is shielded from the sun, it's also in this part of the Earth's magnetic field that's really stretched out and full of very energetic electrons. And researchers, well, now they found out that these electrons could also be helping to create water. And the way they do that is by bombarding the moon's surface and allowing trapped hydrogen and oxygen to bond with each other.
All right, well, on a interesting but also very practical note, reporter Alice Klein has a story out about how chicken hatcheries in Europe are starting to use sex testing of their eggs in order to avoid killing surplus male chicks. Basically, and this is kind of a grim thing about the egg industry, but only the females are useful if your goal is to create eggs for people to eat. So this leads to billions of male chicks being killed after they hatch.
Yeah, I guess it's a very unpleasant part of the process that we try not to think too much about, but billions of male chicks being killed is quite a hard number to get your head around.
And with that in mind, several countries have now banned this process of killing male chicks. Germany, Australia, and now France too. But it still leaves hatcheries with this problem of all of these chicks that can't lay eggs. So they're starting to use genetic tests. They're increasingly accessible for commercial hatcheries, and there are now a range of different ways to do this testing of which eggs contain male chicks and which eggs contain female chicks. Processes can include drilling very tiny holes in the eggshell and testing the fluid inside, to even just imaging that looks for physical signs of the chick's sex. And these are all good before the stage at which researchers have detected that these embryos respond to pain, which is good news on the bioethics front, since the eggs containing the males are still destroyed at the end of the day.
Yeah, so I guess it's a somewhat better way to mass produce eggs. Very interesting. So on a very, very different note, this just in, hippopotamuses are really, really bad at chewing their food.
Me too. But it seems really bad to be a herbivore who can't chew. If you're a cow, chewing is pretty much your only job.
Yeah, and actually cows, they are in fact quite good at chewing. And that's because when they chew, and I'm sure you've seen this, they can generate quite a bit of sideways action when they grind their molars. So they literally chew from left to right or right to left. But the thing with hippos is, well, they've barely got any sidewards motion in their jaws. They can only chew in this sort of in a very standard up and down motion. And that's just an extremely inefficient way for such a large animal to get the massive amounts of energy it needs. And so researchers, they've been watching how hippopotamuses eat, and they've now found the answer as to why hippos can't chew sideways. And it turns out that they have these enormous front teeth, and they tend to lock together, and that's what prevents their mouths from chewing laterally.
Do researchers know why an animal like this would even evolve to be so ineffective at eating?
Yeah, well, it turns out those giant tusks, they do a different job for the hippopotamuses, and that's that they are really good for when fighting other hippos. And it seems that in this case, that just takes priority. They can still chew a lot, just not as effectively, but they're really good at fighting.
Every week, we bring you some of the most fascinating news in science, medicine, and technology. But on the Dead Planet Society podcast, we also give Leah Crane and Chelsea White the cosmic power to rearrange the universe, often for the worse. And in the next episode, Leia destroys her arch nemesis, the moon.
So you've blown the moon into little pieces.
Yes.
But now, these little pieces, right, they're still again in each other's gravity field. And so what happens is you've made the world's biggest ball pit.
The biggest, pointiest, worst ball pit ever.
Right, exactly.
I promise there's guaranteed delight, even if you do, in fact, love the moon like I do. That's coming up next Tuesday, right here in the New Scientist podcast feed.
And after all that, maybe you're still hungry to learn about the latest scientific discoveries, ideas, and innovations. Well, if so, the Royal Institution's exciting autumn series of public science talks is now open for booking. Based in the heart of London, the RI has been a home for science for over 200 years. This season sees pioneers such as physics professor and author Carlo Rovelli inspire audiences with the latest from the cutting edge of science. Listen and learn about the wonders of our planet and beyond. Uncover the truth about artificial intelligence in the legendary RI Christmas Lectures, which this year comes from Professor Mike Waldridge. The Royal Institution is an independent charity creating opportunities for the public and scientists to explore science together. The RI is a home for science, and everyone is welcome. Book now at rigb.org. Puzzle maestro Rob Eastaway is here. Now, Rob, he's a man of many talents. He's written several books on mathematics and one on cricket. He puts on amazing shows about mathematics for school children through his company Maths Inspiration. And perhaps most importantly of all, he is New Scientist's much relied upon puzzle consultant. He sources, tests, writes, and advises on all puzzles that appear in our magazine and on our website. And now he's got another book, Headscratchers, the New Scientist puzzle book. Hey there, Rob.
Hi.
All right, so tell us about this book.
Well, New Scientist has been doing a Headscratcher puzzle column for 5 years, and I've been lucky enough to be helping to sort of supervise that since it started. And we just felt now was a good time to sort of pick out the best ones and to share them. And often, actually, a puzzle might be good, but often the solution and the related ideas behind it are even better. So this is kind of a book that's half puzzles, which are fun in their own right, hopefully, but it's half the solutions and the related backstories, which I think are just as interesting. And often a puzzle is an adaptation of a classic Victorian puzzle. We can talk about those kind of things. For those who are familiar with a guy called Martin Gardner, who used to write a fantastic column for Scientific American back in the 1950s, 60s, and so on, it's kind of in the spirit of Martin Gardner, of using puzzles as a means of discovering the joy of recreational mathematics.
Can ChatGPT solve these puzzles for me?
Well, that's a great question. I have begun setting them for ChatGPT, and the good news is that a lot of the time ChatGPT is really hopeless at solving these puzzles. But the thing about ChatGPT is it's really confident. It comes up. I mean, it's unnerving in how fast it comes. You just press return on a question, and within a second, it's got a full solution there. But sometimes it's a completely spurious solution, and you just prod it and say, "Well, hang on a sec, that can't be right." And a bit like Dobby in Harry Potter, it kind of, "Oh, I'm terribly sorry, sir. You're absolutely right. I'm sorry for the confusion," and he'll throw another solution at you, which is also wrong. So it's good. There's still hope for us humans so far, although there are times when it knows the answer, it's seen it before and stuff. So it can definitely solve some, but so far, not all.
I remember when I was a bit more heavily involved with the puzzle column, that something that you would often talk about is those surprising answers that people send in that are sort of technically right, but in a completely different way than you had imagined when setting the puzzle. Can you maybe talk a little bit about those? That seems like the opposite end of what ChatGPT is doing.
Yeah, I mean, it's what makes us human, the creative side, the people who see smart, alternative kind of ways into a thing that you just never thought of when you set the problem. In fact, the very first puzzle in the book was one of my favorite New Scientist puzzles because it's a classic that I'd seen before, but we found new twists on it. You've just taken the numbers 1 to 9, written them each on a different piece of paper, put them in 2 columns. One of the columns adds to 21, the other adds to 24. And your challenge is to move one piece of paper, one of the numbers, to make the 2 columns add to the same result. Now, I'm not going to spoil it by saying what the aha classic solution is. All I can say is that when I showed it to my daughter when she was like 13 or 14, after scratching her head for quite a while, she did something completely different. And I thought, you know what? I'd never thought of that. And now there were 2 solutions. I thought, I better start checking there isn't another one. And suddenly someone came up with a third. When we stuck it out in New Scientist, I think we had 10 or 15 distinct solutions came in. And the joyful thing about that particular puzzle was it creates a different kind of argument, which is when is a solution creative and when is it cheating? What is the difference between creativity and cheating? And you know what the answer is? Nobody can answer that question. It's a fuzzy line. One person's cheating is another person's creativity. What is a rule? What is a guideline? And these are deep philosophical questions that have been brought out by this little number puzzle.
Well, let's get a puzzle in here that we can spoil the answer to. Rob, I believe you've brought us something special just for this podcast. So what's the puzzle?
Okay, and I'm going to credit my friend Hugh Hunt from Trinity College, Cambridge, who came up with this one. This one is actually in the book, but it's a beauty, and folk will have forgotten it if they've ever seen it before. And I want you to imagine we've got a dictionary of numbers. It's a dictionary of every whole number that could possibly exist. And they've been listed in alphabetical order. Now, you can probably imagine this is an infinitely long book because there's an awful lot of numbers out there. 1, 2, 3, 4, 5, but in alphabetical order. Now, I'll tell you, the first number in the book is 8. That's the first in the alphabetically. And the last one in the book, sorry, we're not starting at 1, we're starting at 0. So every whole number from 0 up, because 0 is the last number in the book. Okay. But here's the question. What number comes second? And what is the penultimate number in this infinitely long dictionary?
Okay, I'm thinking about how alphabetically the shortest word is usually first.
Yeah. Now, there's conventions in dictionaries that a space, for example, comes before a letter. So 800 would come before 18.
I think you've really got us scratching our heads here, as promised by the book title.
Yeah. I mean, 4 something is going to be the second thing.
Well, remember, there's lots more
5,
numbers.
5 something.
There's lots of numbers that begin with 8.
Right.
I mean, 18 is going to come early.
But it's every number that could ever exist. This is terrible.
There's a number that exists between 8 and 18, alphabetically, that comes before 18.
Is it 8 billion?
It is 8 billion. That's second. So we've got this amazing book that starts 8 billion. It finishes 0. What comes before that? And it's bizarre that we can name the penultimate number, even though we can't name all the numbers in between.
I don't know, Tim. You're a math guy.
Yeah, I don't know. I can't think under pressure.
2 and 3 and 10 are all T's.
Yeah,
so,
you're good on the T's.
Yeah, it's 2 something.
2 is good. Yeah.
Is there a 2 zillion?
I wish there was a zillion. Zillion is not official. My kids used to say zillion, as do I, but that is not the official. And actually, we have to say that because there are billions, trillions, quadrillions, and so on. There is actually a vintillion, but let's say that in this dictionary we've ruled out those really obscure things. So all numbers are just composites of a trillion, quadrillion, whatever. You don't go any higher than the ones we've all heard of, which is probably quadrillion, maybe octillion. Doesn't make any difference to the answer.
I can't do it. I think, Rob, you need to.
I'm going to. You know what?
Misery.
I'm going to put you. Okay, you may need to note this number down. It is big number: 2 trillion, 2,202. And I know in America you don't use the and there, but I believe it's the case that you can knock the and out and it's still 2,202, which is a really big number. And it's wonderful. It has this really special property of being the penultimate number in the infinite whole number dictionary from 0 to very large number, but not infinity.
That was puzzle maestro Rob Eastaway, and Headscratchers is out this month.
Now, if you're raring to try your hand at puzzles like this and want a chance to win a free copy of New Scientist's new puzzle book, we've got your chance. Rob left us with a few more Headscratchers for the podcast audience. All you've got to do is send us your guesses as to the answers. Okay, get your pencils out. Are you ready? Here's Rob's clue for this week.
Here's a clock one. It's a lovely everyday puzzle with an analog clock, a minute hand and an hour hand. And at midnight and at midday, the minute hand is exactly on top of the hour hand. But what I want to know is between those two times, just a second after midnight, a second to midday, between those two times, how many times are the two hands perfectly overlapping?
All right, you heard the question. Between midnight and midday, how many times are the minute hand and the hour hand perfectly overlapping? We want you to send us your answer by email to podcasts@newscientist.com for a chance of winning a copy of the book. And if you want to do a little extra credit, we'd love to receive a little audio clip of you telling us your answer, which you can do using the voice memo app or voice recorder app on your phone. And again, the email address to send that is podcasts@newscientist.com. We'll reveal the answer next week with a shout out to everyone who guessed correctly, as well as a new puzzle for you to try your hand at.
Now, there is an ongoing space race among companies such as SpaceX, Amazon, and OneWeb to launch thousands of satellites capable of providing internet service to almost anywhere on Earth. But such plans carry a huge environmental cost, starting with all those carbon emissions from rocket launches required to put the satellites into orbit. Technology reporter Jeremy Su is here to talk about the first study ever to compare the carbon footprints of these satellite swarms. Hi, Jeremy.
Hello, Tim.
So, how big of a carbon footprint are we talking about?
Well, the conservative baseline estimate suggests that the carbon footprints for each person using these satellite internet services can be 14 to 21 times higher than the carbon footprints of internet subscribers using, ordinary land-based mobile internet. This calculation mainly accounts for rocket launch emissions such as carbon dioxide and carbon monoxide. But then there are the worst case estimates that include the possible impacts of additional rocket launch particles such as black carbon and water vapor exhaust. And when those are factored in, the carbon emissions for these satellite internet services may actually be 31 to 91 times higher per internet subscriber.
Ooh, that is quite a lot of extra carbon. I guess that's what you'd expect with a rocket-based one, rather than one that is not based on a rocket. Is it the same for the different companies? Does it matter who's launching your satellite internet?
Yeah, it does indeed matter. SpaceX's Starlink actually seems to have the lowest carbon footprint per internet subscriber, which is mainly because Starlink is projected to serve the largest number of customers, and so the emissions per user are lower. But Amazon's planned Kuiper service has the second biggest carbon footprint in the baseline scenario, or the biggest carbon footprint in the worst case scenario. This is mainly because Amazon plans to launch its satellites using Europe's Ariane 6 rocket that uses solid fuel propellant, and solid propellant emits much higher amounts of these potentially impactful particles, such as black carbon.
So, because the study focused on the carbon emissions from the rocket launches, what happens when all those satellites are finally actually orbiting the Earth? Are there any other environmental impacts to worry about just from them being there?
Yeah, that's actually a really important point, which is actually not covered in this study, but the studies can be seen as a first step toward understanding the overall carbon footprint for satellite internet services. So it doesn't include, for example, emissions that come from manufacturing those thousands of satellites before launch. And when the satellites are ready for planned retirement in 4 or 5 years, they're designed to burn up in the Earth's atmosphere, which will generate even more carbon emissions.
4 or 5 years on a technology lifespan, I'm sorry, that just seems so disposable for something that you're launching into space. And I'm already kind of not a fan of these huge satellite constellations anyway, I will admit that, partly because of that separate issue where, their brightness is making it harder for astronomers to observe the night sky, or, even for ordinary citizens to look up at the night sky and enjoy it being dark. But yeah, give me the sales pitch again. Why are these things useful and to whom?
If we look at Starlink, which has already launched almost 4,800 satellites and currently reports having more than 1.5 million customers, it's providing satellite internet to ordinary consumers who may live in more remote areas, but also some commercial customers, such as ship operators who might need service in the middle of the ocean, and a number of governments. For example, the U.S. military has signed some big contracts with the company, and Starlink's satellite internet service has also been playing a pretty big role in helping the Ukrainian military fight back against the Russian military invasion of Ukraine, because it allows Ukrainian troops on the front lines to coordinate really well with drone operators and commanders. But I agree, it's definitely worth asking where and when we want to consider using satellite internet services and when they provide meaningful advantages over the land-based alternatives, especially because the satellite internet services come with such a huge trade-off on the environmental impacts.
Before we go, it is a very exciting week for us at New Scientist. And I do not mean the Nobel Prizes. No, it is Fat Bear Week. And if you've never been blessed to know about Fat Bear Week, here's wildlife correspondent Corinne Wetzel with a quick rundown of why it's such an important marker of the autumn season.
Fat Bear Week is a joyful celebration of the brown bears in Alaska packing on the pounds to prepare for hibernation. So bears in Katmai National Park right now are eating as much salmon as they can to gain a nice layer of fat so they can make it through the winter. There are photos from the beginning of the season before they pack on all the pounds and photos at the end, and the bear with the biggest, fluffiest glow up usually wins Fat Bear Week. And online voting has already started. It's bracket style. I'm personally rooting for Holly. There's backstories on the bears. You can read about them. Yeah, it's pretty incredible.
When will they decide the winner?
The winner will be announced next Tuesday, so stay tuned. At this point, bears are getting eliminated right and left, so you should cast your vote on a daily basis if you're really invested. But the victor will be crowned next Tuesday, and there will be, I guarantee you, a very surprisingly hilarious chunky photo of a bear that comes along with it.
Well, we'll make sure to let everyone know about that next week. Check our show notes where you can learn more about how these bears know it's their time to shine, gastronomically speaking, plus how to follow the competition and vote for your favourite ursine foodie. There's even a webcam where you can watch Katmai's brown bears fishing and feasting. That's all in our show notes or at newscientist.com/podcasts, and we'll be back next week with the results.
That's it for this week. Thanks so much for listening. You can find all the great journalism we talked about today in the show notes, and you can subscribe to this podcast on whichever app you're listening on.
And as always, if you like the great stories we're bringing you from the serious to the silly, please give us a rating or review on Spotify or on Apple Podcasts. We'll be back next week, but it's bye for now.
Bye.
This podcast is produced by OG Podcasts. Find out more at ogpodcasts.co.uk.